So the goal in this demonstration is to construct a convincing argument that all triangles with the same base and same height will also have the same area. Over here on the left, you'll see that the base of this triangle is 4 units. The height of this triangle is 5 units. The area formula for a triangle is to multiply the length of the base by the length of the height and divide that by 2. That area formula is borrowed from the right triangle or half rectangle. Now, what's interesting is that when I change the skew of the triangle from a 90-degree right triangle over to something more oriented visually to the isosceles triangle, this area hasn't changed. The area remains 10 units. Now, without changing the base or the height, I can make the other, I can make the reflection of that right triangle with a base of 4 and a height of 5. The area still hasn't changed. I can even go outside the triangle with that perpendicular segment or that height segment, where height is perpendicular to the base in this example, or perpendicular to the line that contains the segment that is the base in this example. Height is still 5, base is still 4, area is still 10. Now maybe that won't always work. Maybe if the base is 3 and the height is 6, my area now is 9. And when I change the skew back to the isosceles triangle, the area is still 9. When I change it to the right triangle, the area is still 9. And when I change it to the reflection of this right triangle, the area is still 9 square units. So this will work when the base is 4 and the height is 5, and when the base is 3 and the height is 6, but maybe it's only working for whole numbers. When the base is 3.7 and the height is 1.7, the area formula hasn't changed for this triangle. I have an area of approximately 3.145. But what if I change the skew over to the isosceles representation? My area hasn't changed. Over to the right triangle with the 90-degree angle on the left, my area hasn't changed. Over to the right triangle with the right angle on the right, my area still hasn't changed. And even when the height is outside of this triangle, the area doesn't change. All triangles with the same base and height will have the very same area. So let's see if we can get some clarity on the height of a triangle. On altitude, sometimes we call the height of a triangle an altitude. An altitude is the perpendicular segment from the vertex to its opposite side. In geometry, an altitude of a triangle is a straight line through a vertex and perpendicular to a line containing the base. And let's see if there's any interesting drawings here. These are 3 altitudes. According to the definition, it is a segment drawn from the vertex perpendicular to the line containing the opposite side. Vertex, perpendicular to the line containing the opposite side. Vertex, perpendicular to the line containing the opposite side. So it is not required that it is a vertical segment, only that it moves from a vertex and travels perpendicular to the line containing the opposite side. And it is the obtuse triangle for which we clarify that it's not just perpendicular to the opposite side, but it's perpendicular to the line that contains the opposite side. So here's another illustration of how triangles and height relate to each other. How does the triangle relate to what we're going to start calling the related rectangle? So the related rectangle is created using the base and the height measurements. Of any triangle. Now, this GeoGebra illustration will let me move point E along the line containing segment CD. And here, both DB and CA, because they're rectangles, have the same length, and AB remains the static base length. So this related rectangle goes with any triangle with this base and height. So for any new triangle, we create a related rectangle that has the same base and height. Let's look for a perpendicular line through F, perpendicular to GH, and there's our height. Let's create a line segment. First I need an intersection point, so I'm going to highlight these two. And then a segment from F through I that allows me to turn off this line. Well, that's interesting. It doesn't want to show up outside the triangle. Okay. So let's put a line here. We need the line that contains GH. For the moment, I'm going to turn off the triangle. I'm going to delete the segment, and I'm going to create a new segment from F to I, and I'm going to put the polygon back on, I think. Still getting stuck in there. But we would create a rectangle using this height and base GH. So what I'd like to do is take segment GH and translate it by a vector. So if I can highlight segment GH, translate it by a vector from here to here, I can create the related rectangle. And the area of that rectangle will always represent twice the area of the triangle related to it. So I'd like you to keep in mind the idea that there's a related rectangle created using the base and the height measurements of any triangle. And we will use that to find the area.